Okay, let's continue on our way through the Brayton cycle. There's a lot here. So the two major application areas for gas turbine engines are one, aircraft propulsion, woo, aircrafts, and two, electric power generation, which affects pretty much everybody. Now, the highest temperature in the cycle is always limited by the maximum temperature that your turbine blades can withstand. Now, we have made better and better turbine blades. We're finding better and better superalloys. But this is what limits our pressure ratios that we can actually use for cycle. Because what we saw last time was, yes, the higher our pressure ratio, the more efficient our system. But if we have a max temperature that we cannot go above, there is an ideal pressure ratio to get the most amount of work out of it. I'm just going back to it. And I went too far. Right here. So this is the ideal pressure ratio for this particular set of temperatures. 1000 max, 300 min. As a note, since 300 Kelvin is roughly room temperature, atmospheric temperature, I can't really go much below that unless I'm going into Antarctica. So I have to take this into mind when I'm using these cycles. So another thing we have to think about is that air that we're pulling in is our oxidant for the combustion of the fuel. But it's also the coolant, okay? We use it to cool our turbine blades, actually. We have, so if I'm doing, so look at my, turbofan. What I have, here's my turbofan, here's the combustion chamber, here are the turbine blades over here. Here's the compressor over here. And what I'll have is I'll have some of the air go through here. But I'll also have some of the air go through here. So it splits at the very beginning. It splits at the very beginning, and I have some that's used for cooling, and the rest is used for powering. So we have to be very careful about that when we're using these cycles, that we have as much work being produced as possible without melting down our compressor, melting down our turbine, because then plane doesn't fly anymore. We don't want that to happen. Another thing I mentioned was that there is some work that has to go into running our compressor, because that doesn't run itself. It is doing work on the fluid. And so what is powering that? That is our turbine. We have to have our turbine to actually run the compressor to be able to get anything started in the first place. And this fraction of the work that's running to help the compressor, so back work over my network, that's what's called our back work ratio. Some of it goes to the compressor. We want to make that as small as possible if we can, or make our network as big as possible. Either way works. Either way works. Okay, let's see. A few more things here. So, gas turbines, how are they being developing? Well, one thing we're trying to do is we're trying to figure out ways of increasing our turbine inlet temperatures. So that's just making, how can we make combustion as efficient as possible? Are there better fuels so that we can get it hotter? And also, are there better metals, better alloys so that they can take hotter temperatures? The second thing is simply trying to say, well, we have a compressor, we have a turbine, we're pretending like they're isentropic. They aren't actually isentropic. There's always going to be inefficiencies. So can we reduce those inefficiencies? Can we do it? I hope so. The other thing is we can then add different modifications to the basic cycle, which is done a lot. Intercooling, regeneration, recuperation, reheating. What's all that stuff? We're going to get to that over the next few sections. We'll be in the Brayton cycle for a while. We're trying to find different ways of fixing things. Now, these last ones are the ones we're going to focus on in this course. The other ones are ones you'll have to go into material science. You'll have to go into more, get your hands dirty building things to actually begin designing those. And the last thing I want to talk to you about is those deviations. Like I just mentioned, that our turbine and our compressor are not actually isentropic. Like we say they're isentropic, but actually they aren't. And so because of those irreversibilities, we're going to have heat loss, we're going to have pressure drops, we're going to have entropy increase, like you can see right here. And figuring out how to deal with that is important. Now, I don't expect all of you to get a handbook or something and find out what these efficiencies are, or to go and start measuring things, go find the turbine and measure it yourself. Luckily, what the problems will do is they'll usually give you the compressor efficiency and the turbine efficiency, which is saying how close to our ideal isentropic situation is it? And that's going to be a ratio here. A ratio of the difference between the perfect case and the actual case. Actual case and the perfect case. It's opposite for either one because one's a compressor, one's a turbine. So what is the difference? You can see in both cases we're still starting from the same point, beginning here and beginning here. And we're just saying how far does it deviate from that. Or if we want to put it slightly differently, what we can see here is that the height difference between these two, and this is roughly proportional to a change in enthalpy, we're saying constant specific heats. That is bigger than the height change from here. And so that's why the ratio is reversed for each one. The bigger is always on the bottom. So you'll use that to then find what your actual enthalpy is for a system. And we'll solve several problems using this process. So don't worry too much. I will show you exactly how to do it. But this is how we're going to take those inefficiencies, those irreversibilities, and begin to put it into our problems so we can actually start solving more realistic scenarios. Okay, I think we have an example next. Yes, we do. So I will see you all next time. Bye-bye.